Hey everyone, welcome to my first Houdini tutorial. This is going to be a somewhat long form, kind of hour-long tutorial. We're just going to go through building from scratch this Vellum grains character disintegration technique. So we're going to be importing a character animation, converting him into grain particles, simulating, setting up all the different physical properties of the simulation, the clumping behavior, the friction, going through some debugging and making some improvements, getting a nice high resolution, high particle count kind of final results. So I hope you came prepared. I hope you have your cup of coffee ready to go or whatever you need to kind of study and hang out for around an hour or so. The scene doesn't get too complex. This is the end result right here. We're going to be building it from scratch in a little bit. There's a little bit of VOPs, kind of a quick network here. It's a good, if you're just getting started with VOPs or you're just getting into DOP network simulations, this is a really good starting point or entry point into those areas for Houdini users. If you're just getting started with Houdini, I do go through everything in a lot of detail and try to break down the reasoning for the certain approaches I use, the thought process behind things, kind of visual tricks and stuff like that, just to get everything looking really good. And if you're a Houdini master, there still might be a few tricks kind of scattered throughout this tutorial that might help you as well. So I hope you enjoy the learning process, and feel free to leave a comment or anything like that if you have any questions. We'll get started setting up our character animation. So Houdini comes with a few of these mocap biped object nodes, and these actually store or they read in motion capture information. So if you look at this animation type, we have different animation cycles. We could play, this guy he's at a sports stadium, he's doing a cheer, so it's useful for the crowd shelf tools. There's some zombie kind of horror film stuff. If you're making an apocalypse movie, that might be pretty useful. And then this injured stuff I like to use for just developing character effects. You do very interesting, like this guy could be emerging from mud. He could be coming out of a swamp or something like that with stuff dripping off of him. So it's just a cool starting point to use. And then these are nice because you don't have to look online at Mixamo or other resources like that. They just come with Houdini. If you send the file to someone else, they'll definitely have these nodes. So I think this injured walk, fall, recover version 1 was what ended up looking the best to me. Just some nuances with the way that he's stumbling and then falling. I just liked the way that looked the best. And the one thing you do want to change is this in-place animation, so that instead of constraining him to be walking on a treadmill, he'll actually be traversing through the scene as he walks. And if you double click on this, you can see everything's kind of dimmed down. The lights are dim. If you tried to go in and change stuff, you'll see you get this permission denied flag. So that's because we're working inside of this locked digital asset, or it's a tool that they don't want you to modify the inside of. So if we want to actually access the SOP geometry, or the points, the vertices, and the polygons and everything of this guy, what we want to do is just make another geometry container, and then this will just be the Walkman, and then this will just be like load character animation. We could just turn that off for right now with the display flag, and then if I use an object merge, we can use this pretty much like the icon is showing, where we just fetch geometry from another container or another object node and bring it into here. So we'll just select our object. We want the load character animation. We want the geo skin, and then this deformed skin. You could do relative path if you want this relative reference. I usually prefer them. So now we have our character. He's in a new empty geometry node, and again, the reason for doing this is because we can modify it. If we select points, I can then grab those and make some kind of circus freak. It's like guy walking around with an elongated spine or something like that. So we could freely edit this as we want now that we've brought it into an empty or a new geometry object. So I'll just get rid of that modification. And what we want to do is turn this guy into grains or vellum grain particles. So if we do vellum configure grain, this is the node that people usually use for taking geometry and then converting it or filling it with grain particles. And you just have to do create points from volume, so then it will know to place them inside of the shape. If I want to reduce the grain size to have more of them, you can see at a certain point we lose areas of the geometry. So at like 0.02, he's completely filled with grain particles, and then at 0.01, a lot of the areas of his skeleton or his volume have been missed. The reason that this happens is because these models aren't intended for simulation. They're more set up for rendering. They're optimized so that his arms don't fully go up his sleeve. This is something that's called like not watertight geometry. Basically, if you put this into a bathtub or any tub full of water, stuff would get in here and it just causes problems. Once this conversion happens at too high of a resolution or with too much precision, it realizes that there's this gap, and then it kind of doesn't know what to do when it doesn't know what's inside and what's outside when it's trying to fill it with particles. So that's what causes that problem. So to fix that, what I usually do is end up going just VDB from polygons. And this will kind of, if you're like working with Photoshop and Illustrator, this is kind of like taking a vector version of him, like points, lines, this is like vector graphics, and then converting it to a volume or like a raster image, like everything's fixed to a grid. So if we just do 0.01 for voxel size, we have a pretty nice detailed capture of him, and you can see this sleeve is filled in. If I go convert VDB, we can go back to vectors or back to polygons. So we went and just kind of converted him to an image and then converted him back to a vector graphics or polygons. So this way we have watertight geometry. All of these gaps are filled in. We might just want a little bit more detail. So if I go to 0.008, you could see his fingers are more finely preserved and his nose and features like that. So now when I plug this in at 0.008, everything is completely captured. The inside and outside of his form is recognized, so it knows what to fill, what areas to fill with particles. So if we go back, we can see this doesn't work, but after we've done our steps, everything works as expected. Another thing that's nice about this is if you do the VDB reshape SDF, you can do a dilation or erosion of the VDB. So this way, if you just want everything to be a bit thicker, you can get like a blobby kind of monster. If you go erode, you're kind of going the other way, and you can have this weird, thin, alien kind of form creeping through your scene. We'll just get rid of that for right now. We don't want to use that right now. So if we just go ahead and play our animation, one thing to notice is that it's quite slow. It's taking five seconds a frame maybe to cook everything. And then he's kind of swimming through these grain particles. Every frame, it's converting and filling him with new grain particles instead of just moving or animating the existing ones. So you can see this causes issues on certain frames, and generally it's just not a good idea to work that way. Whenever you're running simulations, you want to work with a fixed set of points. So if we look on the first frame, we have 108,000 points. And then if I just advance, you can see this disappears, and we're down to 468 points. So not having a consistent point count messes up a lot of operations. So what we can do to fix that is if I just do a time shift node, once we bring in our character animation, and if I actually just delete this $F expression, Instead of playing back as usual, this time shift has just turned into a frame hold. And you could see the other thing it's done is removed this little stopwatch icon. So this means it's a time-dependent geometry. Whenever you move the timeline, it will recook, or there will be new changes to this node or the data coming upstream of this node. So removing that icon basically means this is now static geometry, and you can scrub freely. It doesn't require upstream changes to be applied whenever you're changing the timeline. So we've basically just made a static geometry of our character, and now if I convert all of these steps, they no longer are time dependent as well, because they're below that. But we've lost our animation. So we can bring back or reapply the animation using this pretty handy point deform node. And what this does is basically, again, pretty similar to what the icon is showing. It uses like a lattice or a mesh to deform high resolution or any input in this first input. So if we take these grain particles and plug them in, the next step, it wants the rest, the frozen geometry. And then the last input, it wants the live or animated geometry. So now everything's playing back super fast. We're playing back at like 10 frames a second or something like that. And what this is doing is just looking at the difference between the frozen geometry and the animated geometry and comparing that, the distance between those two geometries, and then just transferring or applying it to this character. You can reduce this radius to make it even faster. Basically, this is how many nearby points it's looking for when it's trying to see the difference of animation to apply. If you go too low, you'll get like some slices maybe, kind of like this, you're chopping up a vegetable or something like that. So it just depends on the scale of your scene and stuff like that. Maybe 0.35 works pretty well for this situation or the scale of this scene. And now we have our character full of sand, full of grains, deforming with our motion capture animation, and everything's a static point count, which is what we want. So we'll just go ahead and name some of this stuff to make things clear and just keep organized as we're working. So this will just be hold first frame. This will just be convert to VDB. So this is just a volumetric representation. And this will just convert to polygons. And this one will be fill with grains, and we'll do deform with animation. This one we could just do like import character animation. So pretty straightforward, just bringing in our animation, doing a freeze frame, a hold frame, doing our conversions, and then binding that back to the original animation. All right, let's go ahead and set up our simulation. So we'll just make a DOP network and wire the first input or the primary input into our deforming or animated grain particles. So we have our character who's walking. The grain particles are constrained or being deformed using the animation clip, and we'll just feed that into the primary input of a DOP network. And then this is empty. It's just like a new folder or a new context that's for dynamics or simulations. So we'll make a Vellum object, and this is what will hold our grain particles. And then we want a ground plane so that they have something to land on or collide with or crumble down onto. And then we can just use a merge node to describe the relationship between these two. So we have the ground plane on the left input, and that's affecting the Vellum particles on the right input. And it looks like we have everything set up by default, but we just need a solver now to actually apply the forces and move things around. So we'll make a Vellum solver. We can just slide that right in there. Then we can use a pop force node to apply gravity. So we'll just plug that into the particle forces input, and we can set negative 9.8 meters per second. That's the standard Earth kind of gravity force. And I'm actually going to make a Vellum source node as well. So it already looks like we're reading in the grain particles the way that things are set up using this node. But the Vellum source node allows you to supply a target path. And this lets you choose a SOP path that the grain particles will use to inherit the animation from. So having this guy starting out walking and then crumbling gradually over time is what we want to achieve. And we need to use the target path or target geometry for that effect. So I'm just going to grab the initial geometry, this expression that just means this dot dot is the parent node, and then 0 is saying the primary input. If you middle mouse button on this, you can evaluate it and see what node it's checking. It just means go up one level, go up one directory, and then use the primary input or input index 0. So I can just highlight this and press Control X to cut it. And then if I go over here to SOP path, I can press Control V and paste it. And we can also paste it into the target path as well. And now when I connect it, you can see we have our character being emitted or sourced into our simulation. In this emission type, we want it to be only once. And that just means create him on the first frame and don't continuously stream or spray particles over the duration of the simulation. If you had like a hose or a fountain or something like that, you would want continuous emission. But for this effect, we just want it only once or on the first frame of the simulation. And lastly, with these constraints, we don't have anything plugged into that input. We could also just delete the expression kind of for clarity. We're not going to be using constraints for this effect or this tutorial at all. So we're just purely going to be using grains, adding attributes to them, and forces to control our entire effect. So if we just go ahead and press the up arrow, we can play our simulation and see what we get. Things are working, our force, our gravity is working, our particles have been imported into the simulation, and things are moving around, they're hitting the ground plane. It doesn't look terribly good. It looks like you just kind of dropped a big sack of marbles or something like that. Everything's bouncing around way too chaotically. Everything's sliding way too far. It's kind of like you're on an air hockey table or something like that, and things are just drifting around forever without any friction. So we could go to the Vellum solver and start to change some of the settings here to control our simulation and make it behave a little bit more like sand, or like this guy is made out of like clumps of sand that are falling apart. So under velocity dampening, I usually set that to like 0.1. This is kind of like a drag force. So it just calms things down a bit over time. You can see instead of marbles, now this is like little, maybe like a squishy rubber or something like that, like little stress balls or something that give a little bit when they hit something. They're no longer preserving all of their energy and ricocheting off of each other like at 100% force. There's some dampening over time. And you see there's still things that are sliding a bit far. So we can just increase some of these frictions, static and dynamic, and that should reduce the energy that they preserve as they're rolling along the ground or just colliding with each other or anything like that. The next thing I'm going to do, if we go to just grain collisions, max neighbors, I usually kind of double that or go a little bit higher. That usually gives you a bit better kind of stacking behavior. So that's each particle is looking at nearby particles for each frame of the simulation. And increasing max neighbors basically lets it look at or consider more particles for each time step or each frame of the simulation. So when you have more neighbors, it's easier for stacking and clumping and things like that. And then lastly, if we start to enable this attraction weight, this is the reason why I'm setting, we'll fix this in a second, but this is the reason why I'm setting things up in this network, the DOP network, kind of from scratch, as opposed to making a Vellum solver at the SOP level. So if we just make a Vellum solver up here, you'll see that we don't have any control over attraction weight or attraction stiffness with the collisions. So this is just more of a general use solver for cloth and Vellum in general. But for more advanced features and things like that, we need to kind of create this from scratch or build it out in a more technical or low-level fashion, just to have access to these parameters. So when the clumping or this attraction weight is too high, you get some instabilities in the simulation. You could see that stuff is just shot everywhere. You could either reduce it, or if you go to the common tab and increase substeps, maybe we'll start with 4, then the simulation can stabilize. You could see now he's kind of melting into like a pool of rubber, or he's already clumping up a little bit. Maybe this is like he's made out of a soft cake or something like that, and just a nice fluffy cake and just kind of melting down, like you dropped a cake the size and the shape of a man. There's not a lot of bouncing or stuff like that. It's just pretty mushy and pretty filthy. So it's close to clumping sand. We might want to change some other stuff. We could maybe reduce that attraction. So this attraction weight, you just leave it between 0 and 1, and this attraction strength, you could go up to like 100 or as high as you want. So to adjust just the clumping, I basically look at this as attraction weight 0 to 1 is like active or inactive, and then I use attraction like a global clumping kind of parameter. So if we go down to just 0.1, we'll get a lot similar to like a dry sand or something like that. That doesn't really stick together that well, and just it's like an hourglass or something like that. Things just sift through and kind of diffuse out, pretty blurry. And then the more we increase this, the more kind of adhesion we'll get. The stickier these particles will be with each other. So maybe 15, maybe we'll go a bit higher and just try to get some bigger chunks that stick together. And then just overall, when he falls down, it leaves a much more interesting kind of arrangement, distribution of the pile when he falls down. Instead of this just being like a smooth, round blob, we have very interesting kind of rigid chunks of his body that are still intact. So now that we've figured out our simulation settings and got them a bit dialed in, what we can do is try to import and link up our animation. So if we look at this target path, this is saying the SOP path to use as the target for the Vellum patch. The Vellum patch also just means grain particles. It just means any Vellum geometry. When points are set to follow the target animation, this path is used. Note that the path will be reevaluated at every substep. So that's nice just for subframe animation or interpolation. But when it says when the points are set to follow the target animation, that's something we can set with point attributes. So I have this nice kind of reference glossary of Vex attributes and the behaviors that they control or how you can use them to influence simulations, the appearance of geometry, how geometry renders, like all facets of attributes in Houdini. I'm trying to compile them here on my website. It's just johnkoons.com/vex. So if we go back down to the Vellum, .vellum attributes, you can see we have this stopped attribute. And in the past, with particle simulations, sometimes people would just set the mass to 0 to stop the solver from moving the particle. But setting this stopped kind of condition, 0 just means it can freely move around. 1 means the position or the motion of the particle or the point is constrained to not move or to not have any motion. 2 could be no rotation, but it can still move around. So for fur, like vellum wires and stuff like that, it might be useful. And then 3 is no rotation or movement. So we're only going to be looking at 0 or 1 for this effect. Because these are just grain particles, we don't even consider rotation at all. And then pin to animation is the more important one, and that's what I was talking about with this target path parameter. So if we set this to 1, then these pinned points, or the points that are pinned to animation, will be updated every frame or every substep to match the target point of this target path's geometry. So just middle mouse button, and this is the input deformed particles with the animation. So changing these attributes, I usually work kind of upstream of this point deform. So this is kind of like working in local space. Basically, before the animation is applied, we can create attributes before the time dependency is introduced or things are moving around. This is kind of like the rest pose, the T pose. It's just easier to define, and like if you're making shaders or doing procedural noises, it will be stuck to the character if you do it before you move it or deform it with the animation. So we use this attribute create node and just make a stopped, if I could spell properly, just make a stopped attribute. We want this to be an integer type. With this sheet, I use this type indicator here, I or S for string, F for float. You don't need to always like define it this way. Once the attribute is defined, it will always know what it is, but I just like to keep using these for clarity. So do an integer data type. That just means it doesn't have any decimals or fractional values. And then the value will be 1. So this is kind of like a true or false statement. It's like computer programming language or whatever. 0 means that the stopped condition is false, so it can move around. And 1 means that the stopped condition is true, so it will behave as stopped or frozen. So if we just want to double check that, just go back to the first frame of the simulation and play our simulation. And you can see as time progresses now, none of the forces are being applied to these particles, because with this attribute create, we've assigned all of them to have a stopped condition of 1. So if we go ahead and keep working, there's this next one that was the pin to animation, and that is saying to apply the target path animation to the grain particles or the vellum geometry. So we'll do pin to animation, and this one we want it to be an integer as well. And again, this is like a true or false, 0 or 1 kind of conditional. So 1 means we will be pinning it to the animation, 0 means we won't be pinning it to the animation. So if I play the simulation now, you can see we're getting the same results as before pre-simulation. So even during simulation, everything matches, which is nice. It means we have success. We've successfully pinned or stuck the animations to the deforming geometry or to the animation, and then we've also stopped them so that the forces and things like that don't apply to them. It's nice, but basically the way that things are set up, nothing will ever change in our simulation. We'll just feed in our animation, and because we're controlling things so kind of forcefully, we don't allow any forces or anything else to happen to them. So we'll just perfectly match the animation, and there's not really a point in the simulation right now. So what we want to do is gradually free or release some of these particles over time. So if I use one of these attribute VOPs, we can use some of the VOP nodes to modify these particles on a per point kind of basis. So if I just take the position and plug it into color, you can see we're getting, let me just bring up my correction toolbar. So we have red for X, we have the X component or the X position that's also being fed in to the color channel or the color attribute. So if you're new to VOPs, this is kind of like working with shaders, like Arnold or Maya, Cinema 4D. You're using nodes kind of like this to just, you would take the position and assign it to the shading color. It's the same idea here, but it's just being applied or running over geometry. So we have a lot more flexibility. We can run this before a simulation and then use it to control our simulation behavior. This is kind of the true underlying power of Houdini, is being able to use these VOPs and Vex wrangles and stuff like that to really modify things on a per point. You have control over things instead of just setting a global slider. You can control attributes and physics properties and stuff like that on a per point basis. So what we want to do is maybe take the relative to bounding box position. If we just take the file as basically our input, and the position we're looking at inside of the bounding box is just the input position, and then we feed that into color, then you can see we're getting this normalized 0 to 1 color channel. So instead of just the raw position height or coordinate, this is being normalized or relative to the bounds of the geometry. So from 0 to 1 on each axis. And then if I do a vector to float, instead of doing the color channels down here to visualize stuff, this is just doing the same idea, but actually to the running it inside of the code and applying it to the result. So instead of just changing the visualization, this is actually changing the values. So we just want to look at the Y component, or the green channel, or the height, the normalized height of the positions of our character. And if we use a compare node, this is like the scales of justice. It's basically another kind of conditional, like I was talking about with the stopped or pinned to animation. And it just gets used to compare whether this number, the normalized height, is greater than this slider value. We might want to do less than. So you could see here, if we're looking at this as white or 1 or true, and black is false or 0, we could animate this over time and say, gradually the stopped condition is going from true to false. And that could be a pretty useful way to control the stopped and pinned to animation. So we're taking those attributes and just over time saying, go from your true condition, your constrained to animation behavior, and turn that off like a light switch, like disable that state and go to 0, just behave freely. So that's how we're just going to start setting up the controls to influence releasing the particles over time. You don't want to animate things inside of this Vex builder. You always want to just click the gear and then do promote parameter, and you want to assign your animation or keyframes up here at the SOP level. So we'll just hold down the Alt button and click on the first frame to set a keyframe. You can see that little timeline turn green right there. And then if we advance maybe 72 frames, it's going to be roughly 3 seconds if we're doing 24 frames a second. Just go down to 0 and click again. So if I play just this animation, you can see over time we're going from white to black. And then instead of assigning this to color, we're creating or defining these stopped and pinned to animation attributes. So if I just go inside of here, I can make a bind node, bind export. And this allows you to assign the output values to whatever attributes you want, instead of just having these few things to pick from. It's kind of like, if we're going back to the shader analogy, it's kind of like setting up AOVs or extra render layers. Like you can write this to any extra layer or attribute or whatever value, whatever kind of holder or variable you want to assign to these attributes. So we'll do stopped. And I can just hold down the Alt key and click to make a copy of that and just keep chaining these together. And we'll do pin to animation. So as this value flows through, it will set the stopped attribute, it will set the pin to animation attribute, and then it will finally set the color. So we're just doing all three of these in one continuous chain. We could also just not override the color at the end. It's a bit sloppy to kind of keep storing visualization values inside of that. So if I just do disconnect, now we're just changing attributes and not changing the color value of the geometry. Sometimes the viewport it's a bit inactive or delayed. If you just bypass that and enable it again, it will clear the cache. And then if I do control, you hold down the control key and you press the middle mouse button, you'll get a kind of persistent node information, and I could click on the stopped attribute here, and then that just gives me a quick visualizer. And if I scrub the timeline, I can inspect the change of that attribute over time. Instead of using the color attribute, I'm just able to create quick visualizers this way. This is a nice kind of handy shortcut. We just click it again, it will go away. And then there's one more thing we want to change before we start our simulation. So again, if we look at this node, the Vellum source node, we were careful to set this target path and the pin to animation attributes such that the geometry would know to follow the deforming or changing point position to match our motion captured animation. But the issue we have is that the pin to animation and stopped attributes don't get overridden, or they don't get pulled in and updated into our simulation over time. So the only attribute is this P attribute, or the point position. That's kind of a special attribute, or it's set up using this target path in a special way to be updated every frame. So if we want to update the other attributes, we can just make a SOP solver. And this will let us explicitly import them and copy them over and update them in our simulation geometry at every frame. So the simulation happens in a feedback loop. Basically, the previous frame is fed back, and then the forces are updated. The solver runs again and moves them, and that keeps happening every frame to give you your simulated results. But other aspects of the initial geometry don't get updated. Like if you change the color, if you change the stopped condition or the pin to animation condition over time, those values don't get updated. So what we want to do is just explicitly do that ourselves. So we can do that with an attribute copy node. And if you look here, we're back in the geometry context. That's the benefits of using this SOP solver. You can just create your own SOP nodes, and you're kind of just making your own little routine that will happen every frame. So you're kind of making your own little set of rules, and you're able to use the SOP nodes instead of having to rely on only DOP nodes that there might not be the capability that you're looking for in that set. So we just make the attribute copy node and an object merge node. So the object merge node will allow us to import the deform with animation. So this SOP has the attribute values changing. If we middle mouse button on it, we were animating the stopped attribute and the pin to animation attribute. And if I use this attribute copy, I can just clear out the color diffuse, we don't need to change that. And if I use this drop-down menu, then we can set pin to animation, and we can set stopped. So these two attributes will explicitly be copied or overwritten every frame using our input animation. Or if I go up back to this level, the results of the attributes from this node will be explicitly pulled in and updated during the simulation at every frame. So if I flipbook these results or this simulation, what this is going to do is it will start to run the simulation, but instead of basically caching things like this blue bar is filling up, it also will save the results of each frame to this mplay session or your mplay window. So it's kind of like doing a play blast with Maya or other softwares, I think like Nuke and stuff, called a flipbook. It's basically just like a cache of your viewport over time. So this is really useful. You can export it to an MP4 file. If you're working remotely and someone says, show me the results of your simulation, you don't need to worry about sending them a bunch of geometry files. That's going to be a big kind of data set to try to transfer over the internet. If you're working on site and the supervisor comes by and happens to just say, like, let me see what you've been working on, you don't have to worry about having a cache that's full and your memory being free enough to store the entire cache. If you're working with higher point counts or more detailed geometry, you'll probably notice, or you've had it happen to you before, where this blue bar starts to get erased. So that just means that your memory is full and you've ran out of cache. So saving things to a flipbook or to this mplay window will just let you kind of store these previews of your animation. It's kind of like an intermediary step. Before rendering, you just want to create these little like drafts or previews of your motion, of your animation. The other advantage of doing things this way is that you're visualizing the playback speed at real time, or 24 frames a second, or whatever your scene playback speed is. So if you're working this way, you need to rely on the viewport being able to update the geometry. Like, a lot of things might be running slowly, such that when you play things back, it might only be playing back at 1 frame per second or even slower than that. But caching things to a flipbook, then when you play it back, you can make accurate judgments on the speed and the motion of your simulation. So now when I visualize the results, we can see everything is successful. We're updating the stopped and pinned to animation attributes every single frame. And by doing that, we're able to release or crumble our character up over the duration of the simulation. So instead of just at the start frame, the animation is carried through, or the animation immediately crumbles, like the two outcomes we set up earlier, we have this nice blend or controlled transition of those attributes over time. So that's the power of Houdini and working with attributes. You just have complete control over the physical properties of all the individual points of your simulation. A lot of other software, they don't let you get to that level of control over your geometry. You're just stuck with a few global sliders that you can animate. But using Houdini, you can kind of really brainstorm and create effects that you have thought of in your head or concepted out or whatever, and you're not really constrained by the software. You can just do anything you want because you have complete control over the geometry. So that's very cool. The last thing is just a small caveat. Some of you might be thinking to yourselves, why isn't he using this Vellum solver SOP? So this is a simplified representation of the Vellum solver. It's kind of bundled up in a little digital asset. So it has this lock on it, which basically means you can't modify the insides of it or change too much of it. So instead of this template where you can kind of make whatever you want, this is more of a pre-built setup for you to use. The reason why I didn't use this is because the collisions tab here, you can see we don't have control over the attraction or attraction weight, like the clumping of the particles. And this has been simplified a bit. So even under the advanced tab, we don't have control over the grain collisions. So things like max neighbors, attraction weight, and clumping behavior can't be defined using this Vellum solver. This is more of a simplified node for cloth simulations. I still use it quite a bit, but just if you know that you need control over the clumping, you're going to have to go in and kind of make your own template and get a little bit more technical for that situation. So that's it for right now. We got our successful kind of first pass or first iteration of the simulation. We got these particles kind of peeling off or clumping up in a pretty interesting fashion. Got our guy, at the start it was an animation like he had too much to drink. He's leaving the pub and kind of teetering, stumbling, catching himself. And now it's like he's not had enough to drink. He's like disintegrating or drying up. He's running out of water. His legs are still trying to find the source of water or the oasis or whatever. And he's like, I can just make it. But he's too dried up and he's just crumbling into dry kind of sand or back into the desert or something like that. He can't make it. So we'll be back in a little bit and we'll be looking at how we can improve things even more, add more detail, and kind of take this to the next level and finalize things a little bit more. All right, so let's get started making some improvements and enhancements to this simulation. So we'll go back to our Houdini scene. One thing I'm going to do to just preview our animation a bit easier is make a blast node. I know earlier I was showing you could hold down the control button, middle mouse click, and click on one of these attributes to visualize the changes. But we can also just use this blast node to do a somewhat similar thing. I'm going to change this group type to points, and then we can make selection sets just based off of attribute values. So I'll set the stopped equals 1. If we go to when the stopped is equal to 0. So basically, when the stopped condition is false or they're released, it will delete them, or for the sake of this, the reason I'm using this right now is to hide them when they're released. So this way I can just play through my scene. It's a bit quicker than waiting for the simulation to happen. It's just an easier way to kind of visualize when things are released by hiding them or deleting the particles. So we'll just say visualize hide released grains. I just have this alongside the DOP network so I know it's not intended to be fed in to the simulation. Now if I go back to this animation, I'm just going to go pin this window on top. And the one issue we had was that his arms were staying attached or kept animating for a while, even after the shoulder and biceps and stuff like that had gotten crumbled off or released. So what I'll do is just press the Alt keyboard button and click. And what I can do with this is make a bit more of a dramatic acceleration. So just over a few frames, we should be able to get his arms completely like released. We might need to change some of these other handles just to get it finessed. Whoop, there it goes. So it's just over the duration of like 3 or 4 frames now, his arms are completely released. So that's pretty cool. Then we have this flatter area. So I think this is going to be nice. I might even extend it a little bit more, just so that there's more anticipation at the start of our simulation. He's more slowly getting, I might even extend, could just move this whole area over. So just much more slowly, his head is getting chiseled off, and then his arms go very quickly, his torso goes. And I'm also going to add another keyframe down here. The reason to do this is just to keep his legs and upper legs and stuff like that attached a little bit longer. So I think it's more interesting to see him walking when you see the knees bending and more motion and stuff like that. When it's just some feet kind of still stepping, it's not as interesting, or it's just a bit more odd to see that part of the animation. So we can use these handles to extend out the legs, and then just over a few frames, his feet and the rest of his shins and everything will be released into the simulation. So we have this kind of funky looking S or bumpy animation curve. We'll do a simulation and just make sure it's looking good. So we'll just do another flip book. The only thing we've changed is just the timing of the releasing of the particles into the simulation. So we haven't changed any forces. We haven't changed the resolution of the grain particles. There's the exact same number of particles. We're just going to try to enhance the look of things by making some tweaks on the sourcing or the releasing of the particles into the simulation. And again, the reason for doing that visualize blast node is just to work more quickly. So you could see updating the keyframes, we were able to do that in just a couple minutes and very quickly kind of predict how those changes would affect our simulation. And now we can just run a simulation and verify the results of that. But if we were making like a keyframe, running another simulation, making another keyframe adjustment, running the simulation, it could have taken us an hour or 2 hours to kind of make those changes. So with Houdini, it's just a matter of kind of setting up your workflow to optimize things. You don't want to waste time running simulations when you don't need to. If there's changes you can make just by visualizing things, it's the best way to go. So it's a bit more interesting now with more of his upper torso kind of preserved. You just see more of the animation and movement of his shoulders. Just adds a bit of intrigue of like, oh, he lost his head. What's going to happen? What's going on with this guy? He's walking, doesn't have a head. And then these arms and wrists and stuff kind of fling off a little bit more realistically. This is just kind of, whoops, falling down. There isn't really a moment anymore now where you realize like, wait, those are still moving, but they're not attached to anything. So we solved that issue. And then if we keep going at the end, I think this is working nicely as well, where we have just a longer moment where you see the legs and knees bending. So before we just had these weird little footsteps that were kind of kicking around, and it just doesn't look that pleasing. But this is more interesting when you're like, oh, it's got these big walkers coming towards you. It's just a bit more horrific, or just adds another level of interest and excitement kind of to our performance of the simulation. So just by changing that release parameter, we're able to make our simulation look a lot better, right? We're able to kind of hide the issues or the artifacts of things chipping off, and then we're also able to just add more better timing to the releasing of things. Animation is all about timing. If you've ever worked with a character animator, they're obsessively changing keyframes, sliding things around and stuff like that. So that's the idea of working with this visualization, is just being able to work more like a character animator, but in the context of a simulation. So we still have this one issue. It's pretty subtle, but we're going to try to fix it. It's just these horizontal bands, these lines that pop out as the particles are getting released from him, or he's crumbling away. The main reason I want to fix them is just because if we're saying this guy is made out of like clumpy sand or mud, kind of wet sand, you wouldn't expect to see these really clean, straight lines. You would want to see kind of more organic patterns. So it just kind of breaks your impression of this material and looks like a bit of a mistake or something like that. So they are getting produced just because every frame we're releasing some particles based off of the height value. So from this frame, to the next frame, that one sheet or layer of particles gets freed and released into the simulation. Kind of like you're slicing squares off of like a stick of butter. You just get very clean geometric patterns. So each time a layer or a sheet of particles gets released, it collides and sometimes it squirts out in an odd fashion and produces those kind of popping horizontal bands. So if we want to fix that, I'm just going to go up before we run our release VOP. We're just animating this value to compare the particle position against the height in the bounding box to go from 1 to 0 and release him or free him into the simulation. So what I want to do with this geometry, so I'm going to use a fuse node, and we're going to use this to start to snap some of these points together. So we do this and we have a reduced point count, kind of like a connect the dots game or a little skeleton or something like that. Now we just have 23 points instead of the entire set of points that was like 100,000. And I can plug this into one of the extra inputs of the attribute VOP. And that doesn't change the results at all. Right now it's not being used. This is just an extra kind of hook or reference that allows us to more easily use this data inside of the attribute VOP. But everything is just getting passed through the primary input and then output into the next step. And all of these extra inputs are just for referencing or pulling in information from other nodes or other data sources. So if I go inside of the attribute VOP, we can get information from that kind of connect the dots consolidated points using the near point VOP. So with this input, we can say input number 2. These are the extra inputs that exist on the top of the node. So this is the easy way you can reference them. And then we want to use our current point position to find the nearest point of that consolidated fused point geometry. So if I just use the color information to visualize that, you can see visually we're getting the point number. So we have point number 0, 1, 2, 3, 4, 5, 6. This is like it's connect the dots all the way through 28 or whatever. So 0 through 22, blah, 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 we have all the point numbers. But this isn't too useful, just getting that point index number. So if we want to get other information from those points, we can just use import point attribute. So you can use this to fetch any kind of information from these points. It might be, right now we're saying the position. You could get the color, the CD attribute. You could get the velocity if you want the motion of those points. But right now, position is fine. So I'm just going to use this same input number 2, and then the point number that we want to get the information from will be the nearest point that we just found. So we're saying from that second input and the nearest point number, give me that point position. So when I plug this in, it doesn't look like it's kind of like still debugging, or this is kind of like we're doing an AOV. But instead of the current point position, you can see we're getting some straight lines. So that's because all of these points are finding the nearest point in the consolidated particles and sharing, or they're all using that same position value. So if we use this position to compare against our height, our animated height comparison, because all of these points share the same near point position, we can delete or free them in large chunks. So instead of all of these using their actual point position, we get a smooth line as it animates down. We switch the position or the height value that we're comparing against. And this way, over time, we delete or release particles into larger kind of cellular chunks. So it's very, very cool. It's a nice little trick we can use. So I'll just kind of organize these nodes a little bit easier. Sometimes it's easy to get out of hand with these VOP networks and just get a kind of big tangly mess. So I'm just going to organize this stuff. Can disconnect color. We don't need to keep visualizing that. And we'll just pull this stuff to make some more room. So we'll just say this one is our chunk centers. So visualizing this, we can set it and define these. Visually, each of these points is going to be the center of a little cell that gets released from his grain particles. And if we want, we could go back to visualizing it using our little blast node that we made. So I could play our animation and just quickly kind of get a nice blocking like preview of how he'll get released or freed into the simulation. If we wanted to change this pattern, we can just change our snap distance, and that will define the cell size or the chunk size that he'll get cut up and released into. In some frames, there's still some horizontal lines. I'm just going to increase this capture radius just to get a little bit of a smoother value. It might slow things down a little bit. That's why I had it a little bit lower, but if we're trying to really clean things up now and get stuff polished, it makes sense to use a more expensive radius. Just more expensive is like more computational time to give you those results. So we'll do another flip book. The only thing we changed right now is just adding our chunk centers node. So instead of releasing things, doing the straight line, the raw comparison of the height, now we're comparing the animated release parameter against the chunk centers height positions. So as we release these particles into the simulation, instead of like slicing off little sticks of butter, we'll get a more organic cellular pattern. And that's just going to make things feel a bit more natural, a bit more organic, and less kind of like geometric, which just breaks the impression of the material that we're trying to simulate. So we should have cleaned up all those little popping horizontal bands. And in addition to solving that artifact or that issue, we've kind of done a little bit of a bonus and added an additional control where we can now very easily define the size of the chunks that we want to be releasing him into the simulation using. So if someone says he's breaking up into too small or too fine of little shards, you can just go to that slider, increase it, and he could break up just into 4 or 5 pieces. If you go back to that kind of connect the dots node and change the snap distance, it's just very easy to define the size or frequency of those cells. So even here, you can see we're just getting a much more natural kind of breakup. No more lines. So we fixed all those horizontal lines or the banding issues. No more slices off the stick of butter. We have a lot more organic, interesting kind of releasing into the simulation. So now that we've fixed all the issues, we spent a lot of time finessing this animation curve, getting the performance or just the timing of our simulation and animation looking the way that we wanted it to, we're ready to move to a higher resolution. So if we look at our fill with grains Vellum node, we can decrease the grain size, and we do this to fill him with more particles overall. So right now we have 100,000 points, or 100,000 particles roughly. I might go from 0.01 to 0.006. It will take a minute just to convert him into more particles. Now we're around 500,000. So we go from 100,000 to 500,000, and then we can go into our DOP network, and I'm just going to go to the Vellum solver. I usually find when you increase the particle count like that, or decrease the grain size to generate more particles, we need a few more sub-steps. So I'm just going to go from 4 to 8. And this is just to continue to have stability with the solver. We have a lot more particles, so we're going to have a lot more interactions between them every frame. And to keep things from exploding or blowing up, you just generally need a few more sub-steps to do that. And then with the velocity dampening, I'm going to reduce that. It just looked like before we had a bit too much energy loss. It would be nicer to see him inherit or preserve more motion from his original kind of walking animation. So with too much velocity damping, it's killing a lot of that motion because it's reducing the energy of the particles every frame. And then under attraction, I'm going to go from 5 to 15 just to try to get more clumping. I want to see some more stuff sticking together, a little bit more rigidity. Right now we have a bit too mushiness. It's kind of like he's Mr. Oatmeal Man, or he's just too maybe jello, or it's just too jiggly. So by increasing that attraction slider, we should just have more clumping, more rigidity in the grain particles. It's a bit more like sand or crumbly or something like that. And then looking at everything that we're bringing in here, if I just press spacebar G to home the scene, we have the ground plane from our simulation that we're bringing in. So if I go to cache this or write this to disk, I don't want to save the ground plane. I just want this to be the grain particles. So if I look at the object merge tab right here, you can see we have this asterisk under the object field. If you right click on the DOP network node, under the spreadsheet, you can see where we could list all of the objects that we have within our simulation. So we have ground plane 1 and Vellum object 1. And I can just type in Vellum star. So this is saying any object that begins with Vellum. It's kind of like a filter. And then we'll just do an attribute delete node. And the reason to do this is just to start to remove some of these extra attributes that the solver creates. When we're going to store this to disk, we don't want all of this extra information on our geometry. It's going to increase the file size. We don't want to store a bunch of extra information that we don't need to use. So if we're going to render these particles, the only information we really need to keep is going to be the point position and the p-scale. So if I just say star, we can use that asterisk again, and that will be remove or delete everything. And then if we want to keep stuff, I can use the up arrow thing or the caret and maybe just type in p-scale. So position, it will always keep that. You don't need to worry about including that, but we'll say remove everything but include p-scale. So we have position and p-scale. And then if I do a file cache, we can use this to actually save the particles or the geometry to our hard drive. So previously, we were just doing the cache. This save things into your memory or the RAM of your computer. But if you want this geometry files to stick around even after you close Houdini, you could use this file cache node to save these to a folder on your computer. I'll just delete the hip name. This $OS is nice. It's just the name of your current node or the operator string. And then I usually do a slash right here to say this is the $hip is the folder that your Houdini scene file is in. So in the same folder that I'm saving this file, make a geometry directory or use one if it exists. And then within that geometry directory, make a folder that's the name of this node. And then within that folder, make a geometry file that's numbered by the frame number. And then I'm just going to name this node Vellum grain, add a space, and do character crumble sim. So if I middle mouse button, I can see the full file path that this directory is going to be in. You just do middle mouse button and it will evaluate, or it will show you what these expressions will turn out to be. So if I save this, start to run this simulation, it's going to take a little while. You just take a break or come back in a little bit. It shouldn't be too slow. You just want to make sure it's not running at like 2 minutes per frame or something like that. So it looks like I'm getting maybe a frame to simulate every 30 seconds. That's not too bad. If it's like 10 minutes per frame or something longer than that, you probably just want to go back and move to a lower resolution, or you have too many substeps, or you need to fix something. It just is too slow of a speed to work at if you're waiting several hours for the results of your simulation, or several days is the worst case scenario. You want to still be working pretty quickly. Before, we were able to flipbook things at somewhere between 5 and 10 minutes. It's a pretty good speed to be working at for changing keyframes and stuff like that. And then moving to your final kind of render quality, you could maybe wait a couple hours for your simulation to run, but you don't want to be waiting a couple days, because if you are spending a couple days simulating stuff, then you run into an issue, you need to fix it, then you need to spend another couple days, and before you know it, you've spent a couple weeks just trying to finish a simple kind of effect. All right, so the simulation finished up. Our cache is done being written to disk. So if I go to the top here, we can just check load from disk. And this way, the file cache node will be retrieving and pulling in the geometry that we just saved out. So you might notice we lost the little sphere sprites that were visualizing the size of these particles. That's just because we deleted everything, all of the visualization attributes and stuff like that. So if we want to bring those back in, we still have p-scale, which records the size or the radius of the particle. I can just use copy to points. This is a special node that knows about the p-scale attribute. So whatever geometry you copy onto the points using this will be scaled using that p-scale attribute. So if we just do a sphere primitive, this is a really lightweight representation of a sphere that just uses a single primitive. That's the type of it is a sphere. So we can copy these onto the points, and it's, like I said, pretty lightweight, so the viewport and everything can load it in pretty quickly. If I press the D key with my mouse over the viewport, we can go to geometry, and under tessellation, if I bring that level of detail all the way down, then we're able to scrub or pan the viewport around, and it can just draw those sphere primitives a lot more quickly. We might want to go in, I could add a little spotlight. This will just give us a bit more lighting and shadows and stuff like that. Make things just presented a little bit more in higher fidelity. And I could also do a time blend node. We'll just put that right in, so after we load the cache in, we can use this to manipulate the playback speed of things. So if I go, instead of shift range to just by speed, I could change my speed to 0.25, and then we're playing things back at 25% of the original speed. Because we're doing that, we're going to run out of time now at the end of our scene. So I can just go, instead of 240, you can go up to like 540. And I'm just going to move my scene view around a little bit more. And then I can right click and do another flip book. So this is a quicker way, instead of finally like rendering everything. This is just a nice way to just visualize everything. You can also export this to an MP4 file. You could save the individual frames out and encode it, or put it into your favorite like video editing software. And then this is just a better way to share your results. If you want to get feedback or comments, you could post this on your Vimeo, your YouTube, Twitter, Instagram, wherever you're sharing your work, Signal, TikTok, OnlyFans, and just get some feedback. Other people can enjoy it. They can give you likes. They can subscribe to you, or however you're sharing and growing as an artist. Just giving people a preview of what you've been up to is pretty cool. So with this slow motion stuff, we're really getting a lot better performance, like all the little details and time that we put into the disintegration timing, like the animation curve, the chunking that we set up with these crumbling things getting released. All of those little bits of like extra effort that we put into things really can get shown off and experienced better when we just play back everything at slow motion. Just everything looks a lot more impressive, just makes things a lot more dramatic, and gives your eye time to catch all of the little details that went into making this effect or this simulation. So slow motion is always just a great way to share your work and kind of make it look even better. And then this lighting that we put into the scene helps a little bit, just show off some shadows. You can pick up a bit more of the shapes better. You could realize like the crumbling, the formation, the pattern, stuff like that things make. Just everything becomes a bit better. And we don't have to render it yet. We can just share our progress doing a flip book like this that just takes 10 or 20 minutes or something like that, instead of spending a day or a couple of days rendering everything that might take a lot longer for that step. So I hope you enjoyed watching this tutorial. I just wanted to give a quick thank you to all of my subscribers on my twitch.tv channel. That's where I go and kind of share a lot more Houdini tricks. I do a lot of live streams, Q&A, and just little demos and tutorials and stuff there. So if you have a chance, you can subscribe to me. That kind of helps support the creation of everything that I do over there, and also this content that you see on YouTube, tutorials and everything like that. All of the time that I dedicate to producing educational material is directly supported through all of these people. Subscribe to me on twitch.tv/JohnKoons. So we have tier 3, Jabram, the boss, the god tier. And the tier 1 members, Cyberslain, Long Walk to Than, Oh Hi Marks, Biznasco, Mr. Wazoo, It's Armir, Royal Ontario Museum, Halo 1 Mike, Dun 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 Dun, Peter Galliard, I'm That Guy Brandon, Dubtronics, Zaxbox, Vegan Nuts, Stasha, Kiran Irugla Bandara, Ruby Yachts, Demon Case, Z8 Editing, Naranjos, Joao VFX, Steve GH, Belkin Design, I am Sean Sullivan, Black Ruku, Gurad, Player 2, Mistaken Tuna, Avin Ashlo Bo, Joseph Mueller Brockman, Corin Yan, Gamma Bassoon, Shades of Orange, Umer Karim, Tuna Karn, MKI Alex, and Iliwad. Thank you to everyone subscribed to me on my Twitch channel. I enjoy hanging out with everyone over there, and again, it helps support all of the creation of my educational material, even the cheat sheet on my website. All of this extra time that I put into creating learning material is directly supported through these people. And if you have a Amazon Prime subscription, you can link it with your Twitch account. You get a free subscription every month, and you can use it to subscribe to me there, and that helps me out as well.